This talk is to be about electromagnetic waves. These waves are tremendously important. I'll try and say something about their nature. In other types of wave, we're concerned with the movement of matter, waves in water, sound waves where the air moves, or waves along a rope or along a spring. There's always matter which is moving. Electromagnetic waves are quite independent of matter. They are the kind of waves that can exist without any matter being there. For instance, the heat and light from the sun is electromagnetic waves, although they're coming across empty space. To a physicist, these electromagnetic waves are almost one half of physics. Now, Faraday intuitively recognized that there must be such things, that if you had a magnetic disturbance or an electrical disturbance, it ought to be sent out as a disturbance into space, as a wave in fact. But he was not mathematical. He couldn't put it into equations. It was the great mathematician Maxwell who first framed the right equations and showed that if there were such things as electromagnetic waves, they would go at the speed of light. In fact, proved that light, whose speed was then known, consisted of electromagnetic waves. What is their nature? May I start trying to explain it by reminding you of two very simple effects. The first one is shown by Faraday's experiment on induction. Here I've got a coil of wire, here I've got a magnet. Now, the effect that we're showing is this, that if the lines of force connected with a magnet are moving past a point, they will set up an electrical field. In this case, the electrical field will try to drive a current around that wire, so that if I move the magnet into the coil or out of the coil, this ammeter here connected with the wire will deflect. If you watch the needle now, in, out, in, out. Faraday's experiment. Now, just notice the nature of this effect. If the lines of force of the magnet cut the wires this way, the force is that way, always a right angle. The electric field is at right angles to the changing magnetic field. The opposite experiment is this. Now we'll move the electrical charges, the electrical lines of force, by making electrons run round this wire. In other words, by turning on a current. That again produces a magnetic field at right angles. The lines of force cutting this way make a field that way. When Mr. Coates switches the current on, we are effectively making electrons run round these coils this way. The lines of force are cutting the iron this way. Therefore, a magnetic field at right angles, of course, is produced down this way. We magnetize the iron, and so, when the current is turned on, it becomes quite a strong magnet. And picks up all these nails. Well, now, that is the essential nature of these electromagnetic waves. Let us suppose that this is the aerial of a radio transmitting station. The transmitter is making electrons rush up and down this aerial. So you've got the lines of force attached to these electrons rushing up and down this way. That sets a magnetic field this way, just as in this experiment. That magnetic field makes an electrical field. That makes a magnetic field, and so on. Out goes a disturbance into space. The radio station is sending out its message as electromagnetic waves. Here's another way of putting it with the help of this little model. What have I got here? A coil in which I can put an alternating electrical current from the mains. That turns that into a magnet backwards and forwards 50 times a second. The changing magnetic field inside this coil makes a current run in this coil backwards and forwards 50 times a second. There's no connections, you see, this is quite loose. It's merely threaded by the magnetic field. That magnetizes that makes currents run here, magnetizes that backwards and forwards, currents run there, and so the message is passed on. And if I turn on the switch at this end, you will see the current in this wire by this little lamp lighting up, and you will see the message is passed on to the other end, and that lamp will light up too. There. Although there's absolutely no connection between the iron and these coils. Well, now, I put in coils and iron because I want the energy here all to be collected at this end and light this lamp. But we could take away the coil, we could take away the iron. You can have an electrical field without changing, without electrons having to run in a coil of wire. You can have a magnetic field without there actually being any iron there. Take away that, it's same time true that if you have a changing electrical field here, out it goes and will be picked up there. Only much more feebly, of course, because it's rushing out in all directions in space. So that then is the essential nature of an electromagnetic wave. I've got a diagram here which shows the whole range of electromagnetic waves in which we're interested. Here it is, and it's plotted in this way. 1 here on the diagram means 1 meter, waves 1 meter long. And every one of these intervals we go up 100 times. That's waves 100 meters long, 10,000 meters long, 1,000,000 meters long. Going the other way is just the opposite. We go down, that's 1/100th of a meter, 1/10,000th of a meter, right down here to 1,000,000,000th of a meter. It's a tremendous range, going from 10 to the 6th to 10 to the minus 12, 1,000,000,000,000 times. In this range round about here, 10,000, 1,000, 100 meters long, we've got long waves for radio in this region here. These are shorter waves, and down here, where you get down to about 1 centimeter, we have the very high frequency range of radio waves. Coming further over, we get what we call infrared rays, heat waves, the waves whose warmth we feel when we stand in the sun. And when we get down to about 1/1,000,000th of a meter, we begin to see red waves have a wavelength slightly less than 1/1,000,000th of a meter. And the visible spectrum from the red to the blue, which I've drawn here in color, extends over about 1 octave. Blue light is about half as long as red light. Beyond that, there's also light, but we can't see it, what's called the ultraviolet. And beyond that again, we get still shorter waves, soft and then hard X-rays, and then what's called gamma rays from radioactive substances, and beyond that again, still shorter ones that come in the cosmic rays. So there then is the range of electromagnetic waves that we're going to consider. I've got here a valve, it's called a klystron, which is sending out electromagnetic waves just under 1 centimeter in wavelength out of this little horn here. At the other end here, there is a receiver which picks up these waves. And the pickup is shown both by this little lamp here lighting up and by a note. I might say that the note you hear is certainly not the frequency of these waves, which is, of course, very high indeed. These are modulated, as the electronics engineer calls it, to give an audible sound. So when this receiver is picking up the waves, you hear a note and you see that little bulb light up. If Mr. Coates switches on, you will see this horn receiving the waves by this little lamp lighting up and by the noise. You can see the waves are coming from there. I can cut them off with my hand. Now, reflection. If I move this arm round over here, I've now moved it, of course, out of the beam, and so it's picking up nothing. But if I take a mirror like this, I can throw the signal back into it by means of this reflecting screen here, piece of aluminium. There it is, you see, there's the reflection. So it's very sharp. Reflection. Refraction. Here's a prism made of paraffin wax. It's transparent to these waves, although of course it isn't transparent to light. The waves go slower in this prism than they do in the air, And therefore, if I set that now on my table here and move this round, I hope we'll pick up the refracted waves through that block. There they are, you see. Now we can turn this a little. You see it's sensitive both to the position of the prism and to the position of the arm. Polarization. Now this is an interesting effect. We've seen that these electromagnetic waves, the magnetic and the electric fields are at right angles to the way in which the waves are traveling. In this particular case, this klystron is sending out waves which the electric field is up and down. I can show that by means of this screen here. I'll move this round first of all so that it picks up the direct beam. And here I've got a screen of conductors. Now, if I place that in such a way that these conductors are parallel to the electrical wave, they kill it, as it were. Being conductors, a current flows in them to kill the electric polarization. So you will see, if I hold this with the rods vertical, it cuts it out. But if I turn it round and hold them horizontal, it goes through. Vertical, horizontal. Thus showing, you see, that the electric vector in this case is in this direction at right angles to propagation of the waves. Focusing with a lens. Here we've got a perspex lens. Mr. Coates is going to move that receiver back so that it barely hears the waves from this klystron. But if I put the lens here in the path of the rays, it will focus the electromagnetic waves onto that receiver. See? Take the lens away and we don't get the signal again. Or focusing with a concave mirror. Coates has here a concave mirror, and this time I'm going to pick up the reflected beam. I'm going to look for the focus by means of this similar receiver. There is a little horn which will pick up the waves which I can move about. Now the waves are coming out of this sender. They're being focused somewhere out here by that concave mirror, and I hope I'll be able to find the focus by feeling for it with my receiver. There it is, you see. I'm passing through it at about that point there. So you will see that this concave mirror focuses the electromagnetic waves somewhere out here, just as in the case of light. Well, now I'm going to repeat with my electromagnetic waves the very famous experiment of Thomas Young, the pinhole experiment, when he got the interference fringes which proved that light consisted of waves. In the case of Young's experiment, he had to put the pinholes very close together indeed. He had to look at the fringes, which were still quite close together at quite a distance away, because in that case the wavelength of light is so very short indeed. With these centimeter waves, we can do everything on a much coarser scale. Mr. Coates will put two slits in front of the beam of waves. Here they are, these two slits in this screen, and I'm going now to pick up what I get on the far side with this receiver, which I can move about. First of all, I will cover up one of the slits, like that. And now, if I search across the field with my receiver, you will see there just is a patch, a single patch of waves coming through that slit. So, but now if I uncover this slit, now we get two sets of waves coming through and we'll see the interference fringes between those two sets as I move this across. As I pass through, 1, 2, central one, out there. So the interference is taking place between these waves. Well, finally, I want to show you an experiment which measures, as it were, the length of these waves. May I first remind you what we mean by standing waves, and I can demonstrate that again by means of our Binnicombe model, which I've got over here. Here is my Binnicombe model, and I can send waves along it by oscillating this rod at one end. Now, what I want you to notice is this, that if I send a series of waves along this model, and the reflected waves meet the oncoming waves, they produce a series of nodes and loops. Nodes where the rods remain stationary, and loops where they're oscillating backwards and forwards. And if you keep in mind the scale of the waves I'm sending along and look at these nodes and loops, you'll see that a wavelength includes two loops. It's the distance between alternate nodes. Well, now I'll start by sending a series of rather short waves along, and you'll see these nodes and loops. Now they're going to be reflected. Do you see how it's beating in this series of nodes and loops? Well, now we'll repeat it with rather longer waves. I'll ask Mr. Coates to damp our model. So I start with it still again. Now I'll send rather longer waves along, and of course in this case the nodes and loops will be on rather a larger scale. Watch now. Well, now I'm going to illustrate the same principle with my electromagnetic wave setup over here. Here again is my sender, which is sending out these electromagnetic waves. If we take the double slit away and put at the end here a plain reflecting mirror, now we've got the train of waves coming along from the center here, reflected by that mirror and interfering, making beats between the two sets of waves going that way and this way. In this case, the waves are rather less than a centimeter apart. In fact, this is an experiment to measure the length of the waves. And as the waves are about a centimeter long, the beats will be half that apart, actually about 4.5 millimeters. So I've got to look for them rather steadily, and I put my hand on the block like this and move this very steadily backwards and forwards. I hope you'll see it passing through the nodes and loops. So. You'll see they're about 0.5 centimeter apart. You can hear it chattering as I go quite fast. So there, you see, we are actually observing with this what we saw with the Binnicombe model. And of course, these various phenomena that I've been illustrating with these centimeter waves are characteristic of the much shorter light waves and of the X-rays, which are very much shorter still.